The faults. So the faults in a chip can either be a short. So this is a short in the middle. A short in the middle, or it can be an open, right? So where you have your dust cause the chip the line. So for example, this is the short, and you can have an open, so where this is supposed to be a continuous line A, and then something happens, let's say there is a scratch or something, and this will create a break in between. So now this is not connected, this is broken. So this will be an open circuit, and this will be a short. So they only model to simplify the complexity of testing. They can model it as a short, which is a high, and an open circuit, which is a low. So they model the short as a stuck at 1, and the open circuit as a stuck at 0. So because of the manufacturing defect, this line is now open, so A is now stuck at 0. And this one, because it is shorted, so this line is always high, so this is why it's known as stuck at 1. So this is a simple model, which is to simplify the complexity of testing. So we assume this model, which is known as the stuck at faults. So you assume that any line, any wire can be either stuck at 0, which is shorted to ground, or stuck at 1, which is shorted to VDD. So this is a good model which works well in practice. Okay, so let's look at the example in the layout. So as you can see here, this is the layout of the gate, right? You can have a NAND or an OR gate, right? So here you can see there is a dust here which connects the VDD to this poly, this input. So this line is stuck at 1, and this line, so let's say this is A, B, C, D. So D is stuck at 1, and here C, there is a dust here, and makes this line shorted to 0. So C is stuck at 0. Okay, so what do we do when we have this model? So what we want to do is we want to observe and control the lines or the nodes, right? So observability is the ease of observing a node by watching the external outputs of the chip. So you know there is a chip here, and there is the wires inside, and you have your outside world. So this is your output pin, and you can also have some input pin, and you want to find out what is going on in the chip. Alright, so you want to find out what is going on inside here. So you want to observe what is inside here. So we have to this is known as observability, which is observing the node inside the chip via the output. So you connect this node here to the output so that you can watch what is going on. So if you were to do in a breadboard, right, a resistor and a capacitor, it is easy to see if there is any error here. So you can just use a multimeter probe and measure the voltage here. But when you have a chip, it is not so easy. It is so tiny and you cannot access the little nodes inside the chip. So because of that, you have to put special lines or wires so that it is the little point here is connected to the output, and putting this line is making this node observable. Okay, Now the next point. The next point is controllable. So in order to check whether this node is okay or not, you have to know what should be the value. So here you want to know whether it's open or short. So you need to apply some voltage to it so that you know if it is 0 or if it's 1, whether it's shorted or not. So you want to control the node here. So in order to control that node there, you will connect in a input there. So this is known as controllable. Controllability. So you can force a node to be 0 or 1 by using the driving input pins of the chip. Okay, so this is usually easily done for combinational logic. Combinational logic is usually the static gates like the NAND, NOR, the normal ones, which has complementary input and PMOS and NMOS, right? So this is combination logic. The other one is the finite state machine. The finite state machine is difficult because it requires a clock, right? And the finite state machine usually involves Z flip-flop or a JK flip-flop, anything with to do with a clock. So these can be difficult to control. Okay, so how do we test? So we need to do something known as the test pattern generation. So the manufacturing test ideally would check every node in the circuit to prove that it is not stuck. So you have to apply the smallest sequence of test vectors to prove that each node is not stuck. So the good observability and controllability reduces the number of test vectors required for manufacturing tests. And if you have good observability and controllability, then you reduce the number of test vectors, and when you reduce number of test vectors, you reduce the time taken to conduct tests. Okay, so let's look at an example here. What do we do for a stuck at 1 or a stuck at 0? So let's say you have an inverter. Okay, this is the inverter, this is the out, and this is the in. Okay, right? So you know from the inverter, the truth table, this is the in and this is the out. If it's 0, you're supposed to get 1. If it's 1, it's supposed to get 0. Now something has happened during manufacturing and the output is suddenly shorted to ground. So the output is stuck at 0. So when the output is stuck at 0, it will always have the output 0 no matter what is the input. So how do we test this? How do we test whether the output is stuck at 0? Okay, so when you want to test for stuck at 0, you need to apply an opposite test vector. Okay, so if it's stuck at 0, in order to know whether it's stuck or not, you want this node to be 1, the opposite of the 0. So what will make the input to be 1, the output to be 1, sorry. What will make the output to be 1? So the output is 1 when the input is 0. So you will put in a 0 here, right? So the input, if the circuit is not stuck at 0, in 0, and output will be 1. If it is stuck at 0, then when your in is equals to 0, your output equals to 0. right? And your circuit is stuck, and your output is always 0 even though your input is 0, right? So when you put in the input 0, your output is supposed to be 1, but the output is malfunction and the output is 0. So this will test the stuck at 0 fault for the output. So what is your test vector? Test vector is equals to 0 for the input. This is known as your test vector. So let's do another one.